Do you like hard sci-fi? I love hard sci-fi. Is Cixin Liu's three-body trilogy hard sci-fi? Somebody commented to me that Cixin goes so hard that we need a diamond sci-fi category, and I do not disagree. The science across this series is wild, like it goes Looney Tunes, but in a good way. I'm not entirely sure if I agree with the person who decided Netflix and D&D were the best combo to make the show, but here we are. Now here's the spoilers warning so you can decide if you need to bow out now. I'm going to cover the science across the books, but in the timeline of the Netflix TV show. Now the TV show pulls characters and plots from all 3 books, so if you're currently reading them and have not watched the show, then there will be spoilers. What I won't do in this video is spoil any future plot points that have not appeared in the show yet, so if you've only watched the TV show, you're safe, and if you've read all the books, you're totally safe. Now the concepts across the trilogy and the revelations are pretty freaking epic. I was thinking about these books long after I was reading them, and I actually couldn't read or watch any other science fiction for a while either. I watched a lot of NCIS, read a lot of Jane Austen. It just takes time to really appreciate the layers of detail that appear in this story. And before we get into this, there is also, just to note that there is also a 10-cent production on Amazon Prime. It's lower budget, but follows the book more closely. Now, I haven't watched it all yet. There's like 30 episodes in season 1, but I really appreciate it staying more true to the story of Wang Mao in book 1. And if you really want something that is set in the original setting, then I would recommend the 10-cent production on Amazon Prime. The Netflix show is a adaptation intended for a global audience, and I enjoyed it. I had many problems with it, and personally, I just don't think that they did the books justice. It has a very different feeling, and that's okay, because it's different audiences. So, you know, some people will love the show, and some people will kind of see some problems with it. Anyway, like I said, that's a personal opinion. It's of course colored by my original feelings and reactions to having read the books. Adaptations are great, we love them, but they can be tricky, especially when you already have an enormous fan base like in place waiting to see if you're going to get it right or wrong. And speaking of accuracy, let's get scienced. This bitter earth. The story starts with Ye Wenji, the Red Coast Project, and a single message sent out into the universe. The transmitter used by Ye Wenji to send the first signal in 1971 is a radio telescope. Now, radio astronomy is a branch of astronomy that focuses on studying celestial objects and phenomena by detecting and analysing radio frequency emissions emitted by objects in the universe. You see, radio waves are a part of the electromagnetic spectrum, and so they are made up of electromagnetic waves consisting of photons that travel at the speed of light. When photons of radio frequency travel through an object, they're less likely to be absorbed or scattered, which means that they can penetrate interstellar dust and gas clouds where other wavelengths of light would be obscured from us. Now, because we're not looking at optical wavelengths, we don't need mirrors. Instead, radio telescopes use large dishes with antennae to collect and focus radio waves. We even have arrays of radio telescopes, such as the Very Large Array in New Mexico. Radio astronomy has led to numerous scientific discoveries, including the detection of cosmic microwave background radiation, the discovery of pulsars, the study of molecular clouds and star formation regions, and the mapping of the large-scale structure of the universe. An interesting feature is that all electromagnetic waves can be manipulated to carry information. It's called modulation. Now, you either modulate the frequency of the wave for FM, or you modulate the amplitude of the wave for AM. When it's collected by a receiver, the wave is demodulated and the information can be decoded and directed to whatever the application is. For example, if you're listening to the radio, it will be converted to a sound wave and you'll hear the information. If you're watching TV, it will be converted to video and you'll see the information. Radio waves are specifically suited to this because they have long wavelengths, so they travel further without degrading, and they have low frequency so they don't interact with too many objects along the way. So a lot of our modern communication uses radio waves. This is also why radio waves are one of the ways we could potentially communicate with an alien species, because they are one of the few means of communication that could potentially bridge the vast distances between stars and galaxies. A significant challenge with interstellar radio communication is the distance. It's not just that it would take years for any radio message to reach another world, it's that the intensity of the signal reduces with distance. So the further away, the weaker the signal, the harder it would be to interpret. In Cixin Liu's three-body trilogy, astrophysicist Ye Wenji finds a way to boost the radio signal so that it is temporarily enhanced using the sun. Sorry to disappoint you, but this isn't real. However, the commitment to the bit is strong. Ye Wenji's paper is called The Possible Existence of Phase Boundaries Within the Solar Radiation Zone and Their Reflective Characteristics, and it was fictionally published in 1966 in the Journal of Astrophysics. And as much as I would love to tell you that this was based on a real paper or real research, it just isn't. However, it is pulling from some real science that we can actually talk about. So starting with solar amplification. Now this is a real phenomena, and it's when a solar burst happens. Radio emissions get amplified. It's just that the radio emissions come from the sun. It can't amplify radio waves that originate on Earth. So the fictional theory is that Ye Wenji finds a way to direct a radio signal to the sun, reflect it off it, and then boost it by combining it with a radio burst from the sun, overall sending out an amplified message. It's super clever. It's not real, but then it is science fiction, and that's what's so fun about it. It's just a really cool idea. You see, light waves can of course be reflected, so the idea isn't completely wild, but can they be reflected by the sun? Now, in plasma physics, we have this thing called a plasma mirror. This is generally used in ultrafast optics and laser physics. It's a thin layer of plasma that can reflect electromagnetic radiation. Researchers can use plasma mirrors to manipulate the reflected laser pulse. Now, the sun is a giant ball of plasma, and it can exhibit some properties similar to a plasma mirror in certain contexts. To be clear, the sun does not act as a plasma mirror the way that they are used in labs. However, phenomena have been observed where the outer layers of the sun can reflect and manipulate electromagnetic waves. And this process is extremely complex, it's naturally occurring, and it is not predictable. I'm just trying to manage your expectations here, okay? Now, I have no idea if Cixin Liu knew about plasma mirrors when he was writing the story, but I can see a link between the science and the fiction, which just makes me so excited always. First thing you need to do is prep a radio transmission. Secondly, you beam it at the sun at the right moment and at the right angle so that the outer layers act as a plasma mirror and reflect the beam towards its destination. So the third step is that it gets amplified by solar bursts, and the frequencies or the radio frequencies that are emitted in these solar bursts, where they match the frequencies of the signal, amplify your signal towards your destination. Again, it's not real. It's not real. I'm not suggesting that this is something that could ever be done, but it's really cool sci-fi. Have we ever actually sent out messages into the cosmos? Yes, but only one was intentional.
This bitter earth.
The Arecibo Message. It was sent out on November 16th, 1974 from the Arecibo Observatory. Now, it was written by a team of scientists led by the one and only Frank Drake of the Drake equation, and it was a one-time only radio message directed towards M13, a globular star cluster about 21,000 light years from us. Their reason for sending the signal was more as a demonstration of the power of the Arecibo radio telescope. It had just been remodeled, and to highlight what a massive achievement this was in science and technology, they held a ceremony and broadcast a simple pictorial message made up of 1,679 bits, arranged into 73 lines and 23 characters. The message contains information about our solar system, about DNA, the human form, and some biochemical information about life. The bits were transmitted by frequency shifting at the rate of 10 bits per second, and the broadcast concentrated the transmitter energy towards a small patch of sky 21,000 light years away, and over 3 minutes sent out a 20 trillion watt message. Any location in the path of the broadcast with a radio antenna the size of the Arecibo would be able to collect the radio signal. However, given that it was a single broadcast, the chances of it being received, decoded, and understood are extremely remote. It was more of a symbolic gesture by the team at Arecibo. But it also raised some questions. Should we be making our presence known? But that's a discussion for another video. But what about receiving signals?
Back in 1977, they detected a sequence, called it the WOW signal.
The WOW signal was detected on August 15th, 1977 by the Big Ear Radio Telescope at Ohio State University's SETI project. Now, the signal lasted for 72 seconds, and it has never been explained. Radio signals are detected by their frequency against background noise. So if you look at a patch of sky with no stars, you'd get a base reading for the frequency and the strength of the radio emissions that you can collect. If you then look at a star, you'll get a peak that corresponds to that star or any other object. The thing is, space is vast. So we have to collect information over a long time from the same source, and we can generally then identify the location of the source and what type of object it is. The WOW signal only lasted for 72 seconds, which means that something happened to send out a short burst of a very high energy radio signal in our direction. Now, thinking back to the Arecibo message, which was less than 3 minutes, it's not entirely unreasonable to think that it could have been sent by a powerful radio telescope somewhere out there. However, it is much more likely to have been some natural phenomenon that just lasted a short time. Maybe a solar burst, a passing comet or asteroid, even interference from radio signals on Earth. If it was an intelligent species out there in the cosmos, people have questioned why it was never repeated now. I like to imagine a group of aliens, standing or floating, who knows, standing around their newly built radio telescope, turning it on and sending out a brief signal across space, not with the intention to communicate, but just to demonstrate to themselves the power of science and technology, exactly as we did with the Arecibo message. Maybe somewhere out there is an alien civilization staring at our message, their very own WOW signal. It's fun to think of aliens. It's not very likely. It's still fun. Now, if we did end up contacting aliens, what would they be like? In the story, when humanity is in contact with the Scifi, the aliens' initial hope is that they will be welcomed by humanity as our rulers. Ultimately, they're an autocratic society. Ye Wenji and Mike Evans want this to happen. They feel that humanity is lost. We cannot save ourselves, so just let someone else have a try. They want to hand the Earth over to the Scifi, so they build their organization, whose aim is to create a welcome committee. To recruit supporters, they use a virtual reality game that is designed to identify people who will understand the problem faced by the Scifi world, who will show compassion for the Scifi people, and display a drive to want to save them, ultimately agreeing that their only option is to come to Earth. So, let's talk about the problem faced by the Scifi homeworld, the three-body problem. The three-body problem in physics refers to the challenge of predicting the motion of three mutually interacting celestial bodies under the influence of gravity. Back in 1687, Isaac Newton developed the universal law of gravitation, which allows us to precisely calculate the motion of two relatively stable bodies. The Earth-Sun is a fairly stable two-body system, and so is the Earth-Moon. In truth, though, this is only an approximation, because while we predict the Earth-Sun motion, we're neglecting the influence of the Moon. Actually, we're neglecting the influence of the entire solar system. So really, it's an n-body problem. And n-body problems cannot be solved. Not by any of our current methods. Now, the three-body problem is a specific case of the n-body problem for three celestial bodies. In this case, three stars. The gravitational forces exerted by each body on the other two result in a complex and chaotic system, making it difficult to solve analytically. This complexity arises from the fact that the motion of each of the body affects the motion of the others, leading to intricate orbital dynamics. Now, there are various mathematical techniques and approximations that have been developed to tackle the three-body problem, things like numerical simulations and perturbation theory, and they can provide useful insights into the behavior of specific three-body systems. But exact analytical solutions for general cases have never been found. So, when you place a planet into a three-body star system, what's going to happen to that planet? For the Scifi, when the planet is in orbit around one star and the other two are far away, it's in a stable era. When the second star comes closer so that it can pull the planet away, it enters an unstable era. When all three stars are close together so that the planet is consistently being pulled between all stars, it's a chaotic era. This chaos and unpredictability means that the ultimate fate of the Scifi planet is to either be pulled too close to one of the suns and falling into it, or to be flung out of the solar system altogether. And so, they need a new home. And they like the look of ours with our one singular star. So where is the Scifi solar system? Is it real? It can only be one place. Approximately 4.37 light years away in the Centaurus constellation is a triple star system, Alpha Centauri, the closest to our solar system. Its three stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, form the basis for the fictional solar system of the Scifi. Now, the three stars of Alpha Centauri do operate as a three-body system with complicated orbital dynamics. However, it's not chaotic. Alpha Centauri A and Alpha Centauri B are a binary system, so they're in a fairly stable orbit around each other, while Proxima Centauri orbits them both at about 430 times the distance to Neptune, or the distance Neptune is to our Sun. Now, Alpha Centauri A is a yellow main sequence star, similar to our Sun. Alpha Centauri B is an orange main sequence star, so slightly smaller and cooler. And then Proxima Centauri is a red dwarf, much smaller and much cooler than A and B and our Sun. At the time that Cixin Liu wrote the three-body problem, there were no known planets in the Alpha Centauri system. But in 2016, Proxima b was discovered, an Earth-sized planet in the habitable zone of Proxima Centauri. There was also a sub-Earth planet announced in 2022, Proxima d, which orbits much closer to the star. Now, we don't yet have the technology to fully explore the potentials of Proxima b, and given that its star is a flare star, it seems unlikely that it will have an atmosphere. But the idea that there could be intelligent life 4 light years away is exciting and terrifying. Let this show be a lesson. Alpha Centauri is roughly 4.3 light years away, which means that any radio signal takes 4.3 years to travel the distance. Now, Ye Wenji sends her signal in 1971, receiving a reply in 1979. It's an 8-year round trip. She then responds, telling the Scifi to come to Earth, so the next response comes in 1988. We don't know the contents of any communication between Mike Evans and the Scifi over the next 20 years, but they can only have sent 4 more messages in that time. So up until the arrival of the Sophons, the communication is limited to a few basic messages. It's enough for Evans and Ye Wenji to set up a cult on Earth, because that doesn't seem to be that hard to do. And it's enough for the Scifi to realize that our technology is much more primitive and we currently pose no threat. We'll get to the Sophons in a moment, but their arrival on Earth allows for real-time communication between Evans and the Scifi. So over the next few months, they learn a lot more about humanity and our culture. Now, it turns out that the Scifi are a species that communicate through thought, so no intentions can ever be hidden. As soon as they think it, it is communicated. and they were unaware that humans are different. Once they learn that human thought is different to human communication, they realize that we can hide our intentions. Now, this means that they realize what humans have told them so far could be a lie. And if we can lie, then they can't be sure of what we intend to do or what we're planning. This makes them afraid of us. And given how humans use the nanofibers in the story, maybe they should be afraid of us. Have you seen this scene? Yes, nanofibers do exist. Nanofibers are fibers with diameters on the nanometer scale, typically ranging from a few nanometers to several hundred nanometers. Now, they can be made from various materials, including polymers, ceramics, carbon, and metals. They absolutely cannot cut through a diamond or an entire ship full of people and children. That scene was rough. They really increased the stakes in that one. Anyway, it's a really cool use of fictional science to do something absolutely freaking horrific. Now, I bet the Game of Thrones dudes loved making that scene. This is probably why they wanted to make the show, to be fair. So now that Murder Death Ship is out of the way, the Scifi are currently 4 light years away, with interstellar spaceships capable of reaching 1% the speed of light. This means that it will take them 400 years to reach our solar system. A problem for the Scifi is our ability to develop technology at an exponential rate. While their development has taken thousands of years due to the chaos of their trisolar system, our growth rate has accelerated, leading us to a technological explosion. Now, if we continue at our current rate, then in 400 years, when they finally arrive, we could be far more advanced than their fleet. And so we go from being bugs to being a predator, which will threaten their survival or their desired dominance over our solar system. The solution they come up with is to devise a way to interfere with our scientific progress and stall our ability to discover new physics and so develop technology comparable to theirs. To do this, they make Sophons. In terms of science revelations, the concept of the Sophons manages to be really clever, really weird, and really goofy all at the same time. There's a reason this book series was called Unfilmable. And I do want to say though, I want to point out that C. Shimuka did an incredible job in delivering the dialogue of that scene, and just her entire portrayal of Sophon in general, I love so much. Popular culture and science fiction love to tout quantum entanglement as faster than light communication. Unfortunately, it doesn't really matter how many times you try to say, well, never say never. It just isn't true. Quantum entanglement is a unique phenomenon that relates to quantum mechanics. So we're talking about the very, 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 very small. So the thing is, it's possible to entangle particles, meaning that you can impose a correlation on two particles, one that will cause them to have specific characteristics. So maybe the same or opposite value for a property. The key here is that we're talking about a quantum property, not just any random property. It's very specifically a quantum property, which is something that can be measured and described by a quantum state, such as spin. Why this is interesting is that you can now separate the two particles to any distance, and the correlation will remain. When you measure one particle, you know exactly what the measurement of the other particle will be. Why this is unusual is because the measurement value is not defined at the moment that they're entangled. So both particles have spin that continues to fluctuate until you measure them. Now, this has led people to imagine that there is some communication between the particles, some signal that one sends to the other to let it know what the outcome should be. It's hard to explain why this isn't true, not in any way that's really going to satisfy you, but the truth is, there is no instantaneous communication between the two particles. Now, Einstein thought way back that there must be some hidden variables, something that we just don't know yet about it that's implemented at the moment of entanglement that causes the behavior. But experiments have proven that this isn't the case. In fact, the Nobel Prize was awarded in 2022 for these experiments. The current result is that the universe isn't locally real. Simply, this means that on a quantum level, the properties and behavior of particles are not fully determined by classical notions of locality and realism. Classical realism, or local realism, is the idea that objects have definite properties independent of observation, and that physical interactions are governed by local causes. So, influences can only travel at speeds less than or equal to the speed of light. This view implies that there is a clear separation between the observer and the observed system, and the measurements made at one location cannot instantaneously affect measurements made at another location. Now, we like to think about the world in terms that we can understand, that we can identify with. So it's hard to comprehend how the second particle knows what spin state it should be in, because it's unlike anything we're familiar with. But particles are not like you and I. They don't have thought or intention. They don't follow our rules, so why should it make sense? The statement the universe isn't locally real is about understanding that at the quantum level, the behavior of particles is governed by non-classical principles, such as superposition and entanglement, which defy classical notions of locality and realism. So while it's hard to understand why, quantum entanglement is not an example of faster-than-light communication, no matter how much sci-fi wants it to be. Now, I normally love when a show or a movie or a book uses science in a clever way, and I would consider this a clever way to get around the cosmic speed limit for communicating across the universe. But I think using it just adds more fuel to people's speculations. We all love to point out how forward-thinking science fiction has been historically, but this just is not one of those times. Enjoy it as a plot device, but leave it there. Besides, physics isn't over. There are plenty of possibilities for the future, unlike humanity in this show, because for them, physics is dead.
Yes. We are going to kill your science.
Could there be an end to all physics? We know why this happens in the book TV adaptations, but I wondered, in the real world, could there ever be an end to physics? What I'm about to say is entirely speculative, because we can't predict what the future holds for physics. How our technology will develop and what insights that could bring, we just don't know. But we can consider a few factors. So when it comes to technology, there's kind of a circular connection, because breakthroughs in research lead to more advanced technology, which in turn leads to new breakthroughs in physics. Think about the LHC at CERN, the James Webb Telescope, the ITER fusion reactor. These are all tools that we can use to explore science beyond what we know. But in order to do that, we had to build and develop technology that didn't exist. So you need new physics research to help us build the next particle accelerator, which we need to discover new physics. So as long as we can continue to create this technology, research can continue. If we reach a cap on our technological ability, like a fundamental limit that we can't pass, then our ability to drive progress will be hampered. For example, in order to actually probe small enough to get direct evidence of string theory, we would need a particle accelerator the size of the entire galaxy. And that's not going to happen. From a philosophical viewpoint, then, there are questions about the fundamental nature of reality, the role of consciousness, the theory of everything. Now, these questions, if answered, would provide a more complete description of the nature of our entire universe. But a big factor on this is the limit of human understanding, because, as NDT said, the universe is under no obligation to make sense to you. If we reach the limit in what we can understand, there's no going forward. And then, of course, there are certain limits in physics measurements as well, such as the Heisenberg uncertainty principle or Gödel's incompleteness theorems. These suggest that there are inherent limitations to what we can actually prove. And these, what they're called, are epistemological limitations. These could place constraints on the extent to which physics can actually describe a complete and comprehensive understanding of the universe. Realistically, it's entirely conceivable that certain branches of physics or specific areas of research could have an end, but there are still plenty of unanswered questions relating to the fundamental laws and principles that govern our universe. And when we do get answers to some questions, it rarely closes the topic off. It actually often opens it up to new questions and new mysteries that drives new research to move forward. So as long as there are unanswered questions, physics and the pursuit of knowledge will continue. Okay, you guys, we're almost at the end, but there's one more really cool bit of science that we need to talk about, and that is the staircase program.
This bitter earth.
With the Sophons blocking any new physics from being discovered, all technological advancements have to rely on existing technology. So how can you accelerate a probe to 1% the speed of light using what we already know? For context, our fastest object in space right now is the Parker Solar Probe, and it's expected to reach a top speed of 191 kilometers per second, and that is only 0.064% the speed of light. Going from 0.064 to 1 might seem small, but it is a huge technological jump. Now, Cixin, or Jin in the TV show, suggests propelling a light sail using nuclear explosions. And this is based on a real theoretical concept known as Project Orion. Project Orion was a study conducted by the United States Air Force in the late 1950s and early 1960s, and it was to explore the feasibility of using nuclear explosions for spacecraft propulsion. This concept was based on the principle of the pusher plate. This was a propulsion system where the spacecraft would have a large pusher plate attached to it, and the force generated by the nuclear explosions would be directed against this plate, propelling the spacecraft forward. The whole theory behind Project Orion was proposed by the physicist Stanislaw Ulam in 1946 while he was working at Los Alamos. In 1955, he wrote a classified report which has since been unclassified, so you can read it if you want to. It's titled On a Method of Propulsion of Projectiles by Means of External Nuclear Explosions. Now, their initial calculations suggested that they could accelerate an object to 10 kilometers per second, which would have been an incredible amount in the 50s. It's not very fast in terms of Parker Solar Probe or reaching 1% the speed of light, but they were calculating for much larger objects than a brain in a probe and for much smaller fission bombs. Now, the maths and the details of this report are genuinely fascinating, so I think I might go into more detail in a separate video on this, so don't forget to subscribe if you'd be interested in seeing that one. Ultimately, Project Orion never progressed beyond the theoretical stage due to concerns about nuclear fallout, and then, of course, there was the signing of the Partial Nuclear Test Ban Treaty in 1963. But unfortunately for Team Humanity, Project Staircase fails. One of the cables snaps, altering the trajectory of the probe, passing by all the potential for that speed. To find out how humanity will prepare for their coming war, we're going to have to wait for season 2, if Netflix don't cancel it. Or you can read the books. Or if they do cancel it, you can always watch the adaptation on Amazon Prime by Tencent. So, please don't leave spoilers, though, in the comments for other people. Please don't do that. Now, that's it. That's all I have for you today. I think we covered enough, to be fair. But what did you think? We haven't even gotten to, like, the seriously crazy stuff yet. Anyway, thanks for watching. I'm Abby. I'm a physicist. I'm working on my PhD at the University of Oxford at the moment. And I just like nerding out on sci-fi most of the rest of my time. Follow along if you like this, and let me know what pop culture science you'd love to hear more about. Toodles.
If one of us survives, we all survive.
You'll welcome us, won't you? Without your help, we won't make it. We can't wait to meet you.